Let's look at how the first law of thermodynamics applies to constant pressure processes. These processes are sometimes called isobaric. So the first law, again, is du equals delta Q plus delta W. We are interested in finding out the change in the internal free energy. We can start by looking at the work term. We can define the work as the integral of negative P dV from state 1 to state 2. Because the pressure is constant, we can bring it outside of the integral, and we can actually make this integral happen now, and this is equal to negative P times the difference in the volumes. So the change in free energy, or the change in the internal energy of the system, is the heat transferred at constant pressure plus the work done on the system. And we can write this as the internal energy at state 2 minus the internal energy at state 1 is equal to that heat transferred and then the work term that we just figured out. So P times V2 minus V1. In this equation here, everything except for Q is a state function. So U is a state function, P is a state function, and V is a state function. So we can do a little bit of rearranging here and end up with an expression that says the heat transferred at constant pressure, this is a process variable, is equal to the following: U2, the internal energy at state 2, plus PV2 minus U1 plus PV1. So this is really just a rearrangement of this equation up here, which brought us to this equation down here. So all of this stuff in the parentheses, these are all state functions. And so we can actually define a new state function to substitute for that stuff in parentheses. And we're going to call this H, the enthalpy, and essentially define this as U plus PV. So this is the enthalpy. To say that QP is the enthalpy at state 2 minus the enthalpy at state 1, or just the change in enthalpy. So on this side we have a process variable, on this side we have a state function. This actually ends up being sort of useful. We can then calculate the heat transferred in a constant pressure process by remembering how we defined the constant pressure heat capacity. So we defined Cp as the heat transferred at constant pressure divided by the change in temperature. So now we can rewrite this expression in this way, which gives us dH equals Ncp dt. If Cp is a constant in this equation, then we just end up with delta H equals Ncp delta T. So that's if Cp is constant. If we're faced with sort of a first law problem for a constant pressure process, we can find what we need to know in the following way. This is sort of a summary here. The work is equal to negative P times the difference in the final and initial volume. The heat transferred during that constant pressure process is Ncp delta T, if Cp is constant. The change in internal energy we can find in one of two ways. Either we can sum up the heat transferred and the work done, or, and these give the same answer, we can use this expression here for the change in internal energy.